Now we're starting 9.3, and we're going to be taking what we've learned about polar coordinates, polar equations, etc., and then migrating that over into the imaginary plane. So as a quick review, we want to make sure that we are able to label a coordinate axis. And so when we have one, our x-axis is going to contain the real numbers, and my y-axis has the imaginary. Okay, so let's go ahead and fill that in here. The horizontal axis is called the real axis, and the vertical axis is called the imaginary. All right, so we're going to draw our own complex plane. I just did that, and plot the points corresponding to z equals 3 minus 2i. Now, when I see an expression like this, I can very easily pick out what my real numbers are and what my imaginary numbers are. So this is my real, so that's going to go on my x-axis, and then this expression here is my imaginary expression, which is going to go on my y-axis. So I'm just going to plot it like I normally would a coordinate. So I go over 3 positive on the x-axis and then down 2 on the y. So this would be the point with the expression 3 minus 2i. All right, so polar representation of this complex number can be done by finding the angle and the radius of the circle drawn to the point z equals 3 minus 2i. The radius is called the magnitude. We've talked about that word before. It's just the value of a number. Or we can also call it a modulus. So if you hear either one of those, then it's going to be the same thing. So the magnitude or modulus of z. So z is going to be our value of that polar arm there. And so we're going to denote it with absolute value of z. So it's going to look like that. And if you need to put a little tick mark in the center just so that you don't confuse it with a 2, that'll work. All right. So the way we're going to find this is going to be just like we do with a normal polar expression. So we take our rectangular and we change it to be into a polar version. So I'm going to have z equals the square root of my x value squared plus my y value squared. Now, in reality, what's happening is that you're actually multiplying your expression by its conjugate. And when that happens, you have a perfect square, and what's in between is a negative. Well, the I that gets squared is going to end up changing that sign, and so it ends up being a positive. So when I write x squared plus y squared here, that just means that this is the final version of what happens after doing all of that. And so when I do the y squared, I'm pretty much going to ignore the I. In fact, I'm not even going to write it in there. Okay, so we have the square root of 3 squared plus negative 2 squared. Again, I said I'm not going to write it inside there for the I. So we get square root of 9 plus 4, which is equal to the square root of 13. So that is my value for z. And we know to find the angle that my x and y components are the arms of a triangle. And so one is the opposite and the other is the adjacent. So my y is my opposite and my x is my adjacent. So the tangent of the angle is going to equal my y value over my x value. And so in order to eliminate the tangent from that angle, we take the inverse tangent on the other side of y over x. And I happen to have my calculator in radians. So I'm going to go ahead and put it in, list it as radians, but you can go ahead and leave it in degrees and then leave it in degrees. Remember, when we have a tangent, if depending on what quadrant you're in, if you are in quadrant 1, you're not going to do anything. In quadrant 2, you're going to either add pi or you're going to add 180, depending on if you're degrees or radians. In your third quadrant, you're going to do the same thing. And in your fourth quadrant, you would add 2 pi or add 360. I'm not going to do that just for the purposes of getting through this. When I go ahead and look at the inverse tangent of negative 2 over 3, I get a value of negative 0.588 rads. Okay, so that's my radians. And it is in quadrant 4. Quadrant 4. So this guy right here, I would normally add 2 pi rads to this to get a number between 0 and 2 pi. All right, so let's go ahead and take a look at the definition of what we've got here. Suppose z is equal to x plus yi as a complex number. The magnitude or modulus of z denoted, and we've already said this before, here we go, is the distance from the origin to the point xy. That is, z is equal to x squared plus y squared, or z is equal to z times z bar. So the z with the line on top is actually the conjugate that you're multiplying z by. So when I told you that the I goes away, that's why. But so it's the expression, the initial expression, and then its conjugate. So convert a complex number between rectangular form and polar form. Now remember from our last chapter, our cosine theta is going to be my x and our sine theta is going to be my y. So x is for cosine, y is for sine. Now we're going to take a look at what it looks like in imaginary plane. Okay, so we're going to write it in a polar form that's just slightly different. So we have our initial expression. Of course, this would be r cosine theta plus r sine theta, and then I do have that I because it's an imaginary number. Well, what I can do is a couple things. I'm going to rearrange. So I'm going to take my r and I'm going to pull it out. So it's in both expressions. And then I'm going to put the I in front of my sine. So this is going to be a very standard way that we'll be writing this. So r, and then I have cosine theta plus I sine theta. Okay, and here we have that z value is actually equal to our r. Okay, so we've got an example down here that we're going to go ahead and find our polar form. So I've got, let's go ahead and plot this. Okay, so I have 3 and negative 3 root 3. Okay, so let me figure out what 3 root 3 is. I'm going to pop that in the calculator real quickly, and I get 5.196. So I need to have, I think, a couple more marks on there. All right, so I have 3, so I go over 3, and then I'm going to go down 1, 2, 3, 4, 5, and then a hair over 5. So it's about right here. So this would be 3 minus 3 root 3 with the I sticking on the end. So this is clearly in quadrant 4. So which quadrant? Q4. Find r and theta and then write it in polar form. Now remember, my polar form is this right here. So I'm going to go ahead and find r. So r, which is going to actually also equal z, is going to be square root of 3 squared plus 3 root 3 squared. So what I end up having here is 9, right? 3 squared is 9. And then I have 3 times 3, which would be 9. And then when I square a square root, I just take what's inside. So 3 times 9, that would be 27. So this would be plus 27, which gives me the square root of 36. So that's going to give me a value of 6. So now I know that. And the next thing I'm going to do is find my angle, which would be the inverse tangent of my y over my x, right? So that's going to be the inverse tangent of 3 root 3, that's negative 3 root 3, over 3. And my 3's cancel out. So I'm left with the inverse tangent of negative root 3. And I've seen that before. In fact, I'm going to pull up, I should have a unit circle here that I can pull. There we go. So on my unit circle, I can tell that previously, if I take my y value over my x value, right, this would end up being negative square root of 3 over 1 because the 2's are going to cancel out. So this is actually 5 pi over 3. If you don't have enough experience to know that that's what it is, that's okay. Just stick it into a degree. But I think what you'll find is this comes out to 300 degrees. And so that might be easier for you to see it. So I'm going to go ahead and let's take this picture out. I'm going to go ahead and look at this as the value of 5 pi over 3. Okay, so when I do that, then it wants me to put it into this polar form. So I'm going to go ahead and do that. So that will be z equals r cosine 5 pi over 3. And I don't need to put r. I can put the value that we got, which was 6, right? Because we have 6 here and 5 pi over 3. So cosine 5 pi over 3 plus I sine 5 pi over 3. So it seems like a lot. You guys are used to it for sure up until this area here. And we're just taking that and writing it in a slightly different format. So same procedure here to get your z value or your r value, your magnitude, and then same process that we've used to get your angle. Okay?